So, second lecture, I was pleased to observe that some of you are already using the feedback form. So, yeah, I'm gonna quickly go through the questions because maybe they can be useful for the other people as well. So, someone asked, how hard is it to get the bonus in the homework? I don't know, but I can give you the data from the last year. We had about, wait, I noted it down. Okay, for the first take of the exam last year, which was the first time I was holding this exam, we had 406 people trying the exam the first time, and 255 of them have the homework. So if you split that by half, you roughly get how many groups. I think it's feasible. I can tell you, especially if you're a computer scientist, the first one or two homeworks is going to be, the first one is usually like child's play. It's, I don't know, maybe this year is going to be different. I don't know, but they're manageable, okay? So I hope that clarifies for whoever asked this. Why are the lectures merged this year? It makes it much heavier compared to the previous deep learning for NLP, where we had only 1 hour or so. Yeah, so actually we didn't have only 1 hour last year. I think 1 hour are the recordings. By the recordings, I cut the break, I cut the quiz, which is 20 minutes at least, so whatever. The reason why we merged the lectures is because last year we ended up the course, I think, a couple of weeks before the final exam, and I feel it was a bit stressful for you, for the students. So yeah, this year we'll have double lecture, not every time. I think we have 3 or 4 times that happens. But in return, we finish like a month and a half before the exam. So that means that you can work on the homework, study the other exams. You don't have to, someone can also not attend the lectures, and then he still has 1 month and a half before the exam to even start from scratch. Can we have the slides before the actual lectures? Yeah, for the first time I did not, but yeah, I think you received the email, right? From yesterday, there was the lecture on Moodle. So yeah, they are released usually a bit before the lecture. I'm not from computer science and don't have much programming background except a basic Python, of course. Is there any hope for me? Don't give up. Don't give up. So actually, yes, there is a lot of hope for you. I can tell you that I got much better exams for the non-computer scientists last year than from the computer scientists. Like we have people from cognitive science, from psychology, some engineers who tell me, oh, I just made a quick Python course. I don't know anything. Because those people usually take the exam more seriously and they study more. But the computer scientists are a bit overfit. They try to, oh, I'm going to memorize all the exam from the past year and, then I'm going to be good. And then they get 3 or something. So yeah, I think it's doable. Connected to that, I had bachelor students who took this exam and they passed it. Some of them less brilliantly than their master colleagues, but if you're taking this as a bachelor, you have a lot to catch on. But just a little fun fact, one of my TAs last year was a bachelor student and he got like 1.3 or 1.7 on the exam. And he did not attend the lectures, just say after being a TA, can I take the exam? Of course, he was not involved in preparation of it was the retake, he was not involved at all. He just went and gave it. So, it depends on who you are. Okay, so I guess we can move. I can make this really weird thing. Okay. Any other question before we start with the... Cool. So, also shout at me if I don't see the answer. Sometimes it happens. Okay, so welcome to the second lecture of deep learning for NLP, log linear model. So last time we saw a bit of what NLP is. We saw example of task. We know that somehow we have this data that gets fed in somehow in a model. Today we're going to close the gap. So today we're going to actually see how what we saw before becomes data, what kind of data gets fed into what model to do what, and now we actually train the model. So it's going to be complete, okay? But not before we do another backpropagation example, because it's important, because it's likely that it's going to be in the exam. Imagine if I change my mind, just put something completely different. No, I won't. So, who remembers what's this about? What's our goal in this context? Raise your hand if you remember. Yeah, you.
Deconstitute the function into like single operations.
Yeah, maybe simpler functions. We want to decompose the function into simpler one. But what's the end goal? What do you obtain after this? Yeah. Yeah, it's to calculate the gradient. Why? Because if you have this is not challenging. Also, just for PSA, you don't imagine that at the exam you're gonna find a crazy amount of indentation. I don't want you guys to spend 1 hour on the exam doing backpropagation. This is probably one of the most complex functions you can expect. It's gonna be like a couple of levels of indentation. So we do this because when the function becomes very, very, very heavily nested, we cannot calculate the gradient by hand or with the manual time. So first, as your colleague said, we need to decompose this into smaller function. So let me prepare my thing. Hopefully it works. So what's the most external function we can have here? With the, yeah? Yep, we have the logarithm. So we're gonna say that g is actually this function, we can call however we want, I call it f1, of a made up variable h, and this is just the natural logarithm of h. Then what we have more internally? Anyone wants to guess? Yeah. Yeah, we have the cosine. So after we go on this, and so we're going to say that h, which is the argument of the logarithm, is another function, f2, of another made-up variable called I. I'm going alphabetically. You can do whatever you want. Please don't use like I saw extremely creative way to use don't make my job harder when I need to read the exam. There was a guy who was like f1 of A is B of J is like f3, and I was like, I think it took us like half an hour to correct that. So we have the cosine. What do we have inside the cosine? What's the next? Yeah. Yes, we have a sum. So I'm gonna say that I is this function. Again, I'm going alphabetically, so instead of A and B, I'm using J and K. Now, you could argue that we can now make another additional function, like for example, L, which is the square of another variable. But if you do that, I'm not going to do it today. If you do it at home, you'll realize that it doesn't do anything except adding more steps to the thing. So I can tell you, once you are here, you can already say that you have x squared, so you don't need a new variable, which then you need to call x, and y squared. Okay. Is the DAG complete, or are we missing something? Yes? Yeah, we need the variables. So the variable is gonna be x and y. So now this should be kind of clear how all the dependencies are, right? You also may notice that last time in our example, we had the double dependency. There was like B, I think, that depend two functions at B. In that case, we had to draw two arrows. This time, we don't have to. Now, this is our goal. This is the gradient of this function. So pre-calculated, so we can double check that we're correct. Now, what do we calculate first? Well, the global variable is the derivation of the global function realized by this entire tree with respect to the function which is realized by the node we're considering. So let's say we consider this node. So what is the global function realized by this whole chart? Anyone wants to raise your hand? Yes? What? Yes, let's call so G. Yeah, so it's gonna be the derivative of G. Okay. What is the function derived by realized by this node? Yes? G. So again, this is like the starting. This is nice. It's one. We don't even need to think what it is about. Later, we're gonna need to think what it is about. So let's see. Now it's only also visible. Then we need the local derivative. The local derivative is the derivative of the function realized by this node with respect to its input. So what is the function of this node? Again, we said it's G. G. What is the input of G? H. We saw F1 of H. Here it's clear. It's only one arrow. So derivative of h. But if we want to derive this with respect to h, what is it? Anyone wants to raise your hand? Okay.
1 over h.
Yep, that's exactly it. The derivative is 1 over h. If it's not clear, go back, study a bit of derivation. Oh, by the way, in the exam, if you have this exercise, we're going to give you a derivation cheat sheet because I don't care whether you remember what this derivative is. So you're going to have a list of the most common derivatives, like x squared becomes 2x, the logarithm becomes 1 divided by the argument. So, but you need to understand a bit, right? So now we move to h. Again, we need to derive the global function. Again, is g. With respect to the function realized by this node, that is h. Oh, but wait, we actually calculated already. It's going to be 1 over h. That's okay, but let's also calculate the formula because you're going to need it later. So what the rule set tells us is that the global derivative, it's a sum. And we have to sum as many elements as the output nodes of this. But if you look, how many output does H produce? 1, only G. So we don't have to sum anything. It's going to be 1 element. Now that element is going to be a product. And what it's going to be? It's going to basically be the derivative of the global function, G, with respect to the output node. Guess what? The output node is G. Time the derivative of the output node, which is yeah, but I'm trying to go a bit slower because not everyone could have been this fast. So the output is again G with respect to the node we're considering, H. And you realize pretty quickly that it's basically 1 times 1 divided by H. So it's going to be 1 divided by H. Now we have the local derivatives. Again, it's going to be the node we're considering with respect to the input. So the derivative of h with respect to I. So what is this? Derive with respect to I? Yeah? Yep, it's going to be minus the sine of I. And you see how we're going and concatenating these recursively. Once you get the procedure, it really gets very mechanic. So, for example, now we're going to go to I. Again, derivative of the global function, g, we said it 3000 times, with respect to the derivative of this node. And, well, now you see that basically we don't have anything we can recite. We didn't calculate g with respect to I, but we're going to get there by just applying the same formula. So, again, this is going to be a sum, but it's going to be not because we will have 1 element for each output node. Again, I has only 1 output. So there's going to be only 1 element in the sum. And that's one thing. How is this product? Sorry, how is this element composed? It's a product, which is going to be the derivative of the global function with respect to the output node. What's the output of I? H. And this is going to be the derivative of the output node, again, H, with respect to the node we're considering, I. Ah, but guess what? This one, we calculated it. And the second one, we calculated it. So this is going to be minus sine of I multiplied by 1 divided by H. At some point, it may as be also simple to just say that you need to just concatenate these derivatives, right? But you really need to understand the process. Otherwise, at some point, you make up weird chain rules that don't make sense and you lose points in the exercise. The local derivative, well, we need to derive I with respect to its input. So again, we're going to have I with respect to J and I with respect to K because I depends on 2 variables. So what's J plus K derived with respect to J? Anyone want to see some different ends raised up? Yeah? Yeah? And what's J plus K with respect to K? Yeah, it's going to be 1. And now we keep going. So again, we're going to have the global derivative of J, which is, again, the global function G with respect to this node. Again, it's not going to be a sum because we have only one output, so only one element. That element is a product, which is the global function with respect to with respect to scared is going to be with respect to I, because it's the output node. And then the output node, the Y, with respect to, it's almost right. Sorry? No, it's not going to be the global one. Well, there's going to be I with respect to G. You will be going the opposite way, right? You need to unpack the function. So it's going to be I with respect to J, which is our function. But, oh wow, we actually calculated 1 and we also calculated 2. So we just need to multiply this and it's going to be this one. I actually expanded it, so you say J, H, H, I, J is like the same. You could have just put this as like the of J over the of I. I don't care. And then we're gonna be the local derivative. Okay, what is J? Is x squared. What x squared derived with respect to x? X squared with respect to x is 2x. And you know, we're gonna go, for example, I can show you already without using too much of your time, that this is gonna also be obtained like this. Then we're gonna calculate, you know, y squared with respect to y, which is 2y. And now you have the final one. So variable, we won't have any local derivative because, you know, x and y do not basically produce anything behind, do not get any input. So this is gonna be the derivative of the global function with respect to x, and look at it, this is actually our gradient. So let's see if we can get it. Again, this is gonna be the global function with respect to the output node times the derivative of the output node with respect to x. And again, we calculated the both of them, and we can just recycle it. This is going to be minus sine of I divided by x, sorry, divided by h times 2x. And the same is going to be for y. So this is the end. Now, did you actually calculate the gradient? So this is the function. Let's say, well, it looks a bit different, right? But we didn't substitute yet. We have I, we have H, all those elements. So let's try to substitute until we see if that's actually the this gradient. Now, these are the aliases, and this is what we obtain. For example, by taking the left one, derivative of G referred to X. So substituting Y, sorry, I is J plus K. So this becomes sine of J plus K. Substituting H is cosine of I, so it becomes sine of J plus K divided by cosine of I. Again, we can substitute I, which is J plus K. J and K are basically x squared and y squared. We know that. But what is sine divided by cosine of the same argument? Is the tangent. So would you look at this? We actually obtain the tangent, the derivative, sorry, the gradient. Now, is everything good? We solved it. You see any issue in this whole thing? Raise your hand if there's something that you think it's a problem here. Yeah?
This is a partial of the root for x of b to y.
Oh yeah, but we did it before, right? In the first slide. I'm just substituting here. If you substitute, as I told you, can substitute in the dg with respect to y, you obtain the same thing. You obtain the actual gradient. Now the point is, this function is not great for us. So we want to minimize it. You know, we talked about it in the previous lecture, because if a function can do something useful for us, let's say, tell us if something is positive or negative. If we minimize it, we obtain something cool. But what were the prerequisites of the functions? What function do we want? Does anyone remember? Or the two prerequisites of our functions? Wait. Sorry? Yeah, differentiable how, like somewhere or in any point. We want to be able to differentiate, like to calculate the derivative at any given combination of, in this case, in the case of our function x and y. We also want them to be calculated, like we can evaluate their value, right? So now the questions are, can we evaluate the logarithm of the cosine of x squared and y squared? And can we calculate its derivative? Is it defined everywhere? What's the existence condition? Where is the logarithm, the natural logarithm defined? Do we have any value for which we cannot? Yeah? Yeah, it must be greater than 0. So when you check our function from before, which was like whatever, ln of cosine, blah, 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 blah. The argument of this cosine can become 0. Cosine can become 0. At that point, we cannot calculate the derivative anymore because the logarithm of 0 does not exist. In fact, if I show you the chart of this function and the gradient, you're going to realize that you have these holes, these kind of donuts, where the function is not defined. And you can see also that the arrow, the gradient, has no direction. It just does not exist. So can we make it work somehow? Yeah, of course. We are great at doing dirty tricks. We can say, oh, when it's not defined, I just assume the gradient becomes 0, or I substitute with some approximate function. I change the function, whatever. But we don't care. We're gonna see what works. So I just wanted to show you that just because we can calculate the tree and obtain the gradient as a formula doesn't mean this function can then is great to be optimized. That said, today we see the motivation and basic formulation of a machine learning program, the challenges of NLP. We're gonna cover supervised machine learning, the numerical representation of natural language, how do we convert text into numbers, and why we need to do so, and binary text classification. So let's start. What's the motivation today? We want to learn a simple but very powerful algorithm that does binary sentiment classification. So who remembers what's binary sentiment classification? Raise your hand. I heard a lot from you. I'm gonna raise your hand, guys. I want to hear someone else. Yes? Yeah, so we have a text, like a movie review, like, IMDb. We want to calculate if that text is positive or negative. Is it telling us the movie is great or if it sucks? This model is very famous. We're not inventing it together. It's called logistic regression or maximum entropy classifier. And in fact, it is a single layer neural network. It's very, very simple, but very, very cool once you understand it. And it's basically one of the building blocks of deep neural networks. But what is a deep neural network? Well, we'll see it later, don't worry. So this is the normal, overall generic definition of a machine learning problem. We have a data set. You remember this from last time. We have a couple, pairs, input and output. We build a model which solves the task captured by D. For example, D realizes capturing the sentiment of a movie review. And we have two things. Y hat, which is the model prediction. So if the model is good, we expect y hat to be kind of the same as y. So let's say that if our review is 90% negative, a good model will get 0.89999%, 8777% negative. Yeah. And we have theta. These are the parameters. These are the things we can change while we're training to adapt to the model, to adapt the model to the task and solve the task. And we want to minimize a loss function, which is basically how far we are, how our model prediction is far from the actual prediction. Like if I should produce 90 and it produces 50, we're very far. If we should produce 90 and we produce 85, we're a bit closer. So we're gonna have this L of theta, which is defined as the average, You don't need to focus so much. We're gonna see it later in this lecture, what this means. But first we need to understand the challenges of natural language processing. There are many. The first one is that the human language is ambiguous and variable. And these examples might sound a bit stupid for you, like, oh, I ate pizza with friends and I ate pizza with olives. Unless you're a cannibal, it's clear that there is a difference. It's not so easy for a computer though, right? But also variability. You can say in so many ways the same sentence. You can say, I ate pizza with friends and I share some pizza, my friends join me for pizza night, blah, blah, blah. So this is kind of our course. We are so good at using language. Language evolves so quickly. I mean, relatively quickly if you're a linguist. This works. But we are so bad at formally describing how we use language, right? Describing every rule of how you can combine the subjects and verbs and blah, blah. So the best method for this, for us at least ignorant computer scientists, it's supervised machine learning, which is basically, we have a model, try to infer a pattern and learn how to solve the task from a set of annotated input-output pairs. So basically, machine learning is super good at those problems where the solution is very hard to define formally. Like, it's very hard to define formally what makes a movie review positive. There are so many things. Once you put irony or double negations, cultural difference, in French, you might have a sentence that for most native speaker may sound normal, but is actually ironic. But if you take a person and ask him, oh, is this positive or negative? He says, oh, yeah, that's easy. I can tell, right? So we're very good at annotating it. Human language is discrete. So if we start from the very, very basic element, the characters, a series of characters can form everything, from words, which denotes objects, concepts, really whatever you can make your mind. But character words are discrete symbols, and it's a real problem, which is a thing we have to basically fight with compared to other machine learning domains. Why? Because if I give you pizza and a burger, these are kind of similar words, like it's food, it's fast food, depending if you get it, you have a mental representation of them, and so you know that they are kind of related. But they are just symbols. The meaning is just in your head, and it's very hard to distill for a computer. So compare, for example, the fact that we have no actual relationship. There's no way for someone who sees pizza and hamburger for the first time to even get the idea that they're related, especially for a computer. So think about colors of acoustic signal. If we talk about images, we have actual mathematical functions to turn a color image into a black and white. Like you open Photoshop or Lightroom, that's all functions to modify the brightness, the contrast. We don't have that with text. There's not a quick mathematical function that turns a pizza into a hamburger, or that turns a sweet dish into a salty dish. Yeah, but to us, it's super easy. Or compare sound waves. You can compare the frequency. You have mathematical function to pitch up or down, slow down, add reverb to an audio. We have nothing on that in language. So yeah, this is just what I say. We cannot move, for example, from red to pink with just adding a constant, like it's not a vector. Human language is also compositional and sparse. So again, we have characters which form words, which forms phrases, which forms sentences, which forms paragraphs, which forms pages, which forms chapters, which forms books, which forms encyclopedias, blah, 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 blah. So the meaning of a phrase can be much larger than the meaning of its individual words, right? We agree? And they follow very intricate rules. So if you consider New York, or to look something up, or keep the bucket, or blue chip, these all have different meanings that cannot be aggregated by a single rule, right? It's very hard. So to interpret a text correctly, what do we need to do? We need to go beyond just the symbols, and we need to look at the entire sentence or even the context, like an entire document. A specific sentence may not make sense on its own, but it makes sense if you're reading a book and you knew the charter for 3 chapters, and now you understand why he's saying that. Or it may be known later in the future. Oh, why did he say that? Then charters ensue. Oh, that's why. So in how many ways can we combine words to form different meanings? Basically in every possible way ever. So we cannot generalize from one sentence to another. We cannot define easily similarity between sentences. We can as humans. Like if I show you two sentences, you have an idea. For a machine to formalize a formula, that's crazy hard. And the meaning can even be unknown, right? So because whatever you do, no matter how many sentences you collect, there will always be a sentence nobody never said, that you never saw, and you don't really know how to interpret in the first time. So we give up? No, we don't care. We'll find a way to do this somehow. So we're gonna see why, how. So towards supervised machine learning on text data, it's time for some notation, which, yes?
Something about the previous slide.
Yeah.
So I understand here why language is positional,
Mhm.
but sparse. How would you justify that?
Well, you can follow the Zipf's law, for example. Not all sentences are equally distributed, right? Some sentences are rarer than others. If you put also culture and language, even more. So it's not like we have, I don't know, a pool of 3,000 trillion sentences. There are all the sentences ever said by human being, and they all have the same frequency, right? Also, at any point, you can make a new sentence, even stupid ones, silly ones, but just for the sake of. We can move. Okay. We're gonna look at some notation, which I think should be pretty straightforward and known for you. But let's go for them. So there are scalars. These are values. We're gonna call them X, Y, or B, A, Hugo, Susan, however you want. We're gonna make it bold when there are vectors. So raise your hand if you don't know what a vector is. Yeah, okay. If you're lying, you're gonna see examples anyway. No, not only if this becomes capitalized, they are matrices. Raise your hand if you don't know what a matrix is. Matrix. Okay. Then we're gonna say that this is the index operator of vectors and matrices. So I'm gonna say like x. No, why? Okay. X of 1 is the first element of the vector, or the second if you do zero indexing. Gonna try to be coherent in that. So yeah, just said this. And the same for the matrix, but we're gonna say row and column. So yeah, you should be very familiar with that. We have sequences, so we're gonna say x1 to n is the sequence of vectors from x1, x2, x3, blah, blah, blah. Yeah, the elements. We're gonna concatenate vector this way. So, if we have 1, 2, 3, and 4, 5, 6, and this is A, and this is B. I'm gonna say that A, semicolon, this is semicolon code, whatever, B, is 1, 2, 3, 4, 5, 6. Clear, right? Not scary for now.
Sorry.
Yeah,
I have a stupid question, but
it's okay, no question, stupid.
is it important to differentiate between scalars and vectors in written like notation when we write like an exam or something?
Nah, not. You don't need to make it bold or italic. It's gonna be given. It's gonna be given by the context. Also, I never ask you to instantiate random vector matrix. Usually, you have something, you multiply. That's okay. Note, we are chaotic, so we're gonna use row vectors, not column vectors. So that's gonna be a bit triggering, but I guess all mathematics is gonna leave this course pretty easily because they get too triggered by how messy we are. Yeah, we already see this, right? Multiplying vectors and matrices, you're gonna need this a lot in the course, okay? So consider a vector x, it's a vector because it's bold and lowercase, which has a dimension d in, so R6, so 6 numbers. And then we have a W, matrix W, you can tell it's a matrix because it's bold and uppercase, which has 2 dimensions, d in and d out. And then we have another vector, which is d out. Let's try to do x times w plus b, which we assume that in the first dimension is 3 and the second dimension is 2. Now, remember, very easy rule to when multiplying two matrices, Also vector and matrix, because in the end you can say that you can generalize a vector as a, you know, a matrix which has one dimension fixed at 1 if you really want to. But so if we have two matrices which have dimension, you know, D1 row, D2 columns, and the second one is D3 row and D4 columns, the requirement is that D2 and D3 are the same. So then we can multiply them. And this will tell us that the matrix is going to be D1, I call it 1, times D4. So basically, the result is going to be a matrix or vector, depending what you do, which has the rows of the first matrix and the columns of the second one. So for example, if you multiply a vector, this one is, well, I feel a bit silly, but okay, I'm going to ask you, who can tell me the dimension of this vector? The x1. Raise your hand. How many columns? Yeah?
3 by 3 columns.
1 by 3, actually. So I mean, usually we say row and then column. So this one has 1 row, but 3 columns. Right? Makes sense? So 1 by 3, or you can say just 3. This one has 2 rows and 3 columns. No, sorry. No. Failing in my own thing. This thing has, okay, 3 rows and 2 columns. So which means that the result is going to be 1 row, 2 columns. And that's why, after multiplying it, we can actually sum it to B, which has 1 row and 2 columns, and obtain this. All clear so far? Or like, you know, hopefully it is not triggering you too much trauma from calculus. Okay, another clarification. We often like to restrict our search space of a solution to specific families of functions. For example, as we said, all the linear functions with a specific dimensionality as an input and a specific dimensionality as an output. Another way, all the functions which are derivable and can be calculated everywhere. This is what we call an inductive bias. We are intrinsically limiting the power of our model by saying, oh, we prefer only these functions, because maybe there's a better solution, which is defining another space, which is a completely different function, which is a pain to optimize, and we don't want to deal with it. So in the end, what we do about this? Nothing. I mean, we try to get the best we can. So basic formulation of supervised classification, which is classification, give a label to some data, maybe some text. Supervised, which means we know the answer in advance when training, right? We have the review and also the label, and we try the model to get a connection, a function that interpolates the path from, oh, this is the review, this is the label. We have a high dimensional linear function, which an input dimension and an output dimension, the in and the out, which takes an input x. We're going to calculate f of x with these w and b, which are called explicit parameter, which is what we refer also as theta. These are commonly called the weights and biases. So you can think about it something like, you know, the weights kind of stretches and works where you're moving, and the b adds an offset to it, okay? That's a kind of intuitive way. Where you have x, which has the dimensional input, the dimension of the input, w, which has the in times the out, otherwise we could not multiply it, and b as the out. What's the goal? We want to find w and b, all the values, such that when f gets fed an input like a review, it outputs something like a label, which is as intended. As intended, it means that it needs to be similar to the response, right? So we're gonna see soon what that means. In the meanwhile, we can go with the first quiz. Let's go. Numerical representation of natural language text. So, little recap. We have our function, f of x. We have our parameters, w and b, weight and biases. And we are trying to achieve binary text classification, which means we want a model that somehow takes a test and returns a label, positive or negative. But we have text. We have positive or 5 stars, whatever, and a text, which is a review. But computers do not work with text, not natively. They work with numbers. So how do we convert our data in numbers? Well, on one side is easy. Let's start with the label, positive or negative. Anyone can think of a way to convert positive and negative into numbers? I heard already from you. Yeah? Binary. So yeah, we can convert them to 0 or 1. 0 can be negative, 1 can be positive. You can swap them, whatever. Okay, easy peasy. But what do we do for the review? How do we convert our review into numbers? We're gonna get, I know you know, we're gonna go there step by step. So we need to ask ourselves first, what is a word? So what is a word? Is your hand? Well, if there are linguists now, they're going crazy on this. Anyone wants to guess? It's okay, guys. You can guess. It's just to yeah.
String of letters.
String of letters. That's good. So something more, yeah.
It's a small meaning unit of language.
Yeah, small meaning bearing unit of language, which is very bit more philosophical, you know. In a yeah.
To take this a step further and say it's a series of tokens.
Series of tokens. We're gonna see what tokens are. Yeah.
Like labels, we have directly decided to call everything as this word labels.
Yeah, I mean, it can be a human decided upon label. I will go with I think there's enough definitions. There are many ways, right? Very simple definition is a word which is separated. A word is separated by white spaces, for example. Does this work? Not really, because then we have examples like this, right? Are these different words? Because if we follow white space separation, then these are 3 different words, but they are not really. So another way we can do this is just separated by white spaces or punctuation. Maybe it's not perfect, but let's work with that for now. So we have this little thing called tokenization, which is the process of splitting text into tokens based on white space of punctuation. So this is how we segment our text. Like we have the entire sentence and we extract the single elements. So in English, it's quite simple. If you go, I don't know, in Hebrew or Arabic, that's already a bit problematic. Sometimes they don't use the white space. For Chinese, for example, good luck. In fact, if you're interested, go check the Chinese NLP. It's a whole different world, right? Like it's now I think we're filling the gap with the large language models, the recent models. But for a long time, processing Chinese text, their whole tokenization process, their all different rules was quite challenging. So, tokens. Cat and cat have the same meaning. Are they the same word? Yeah?
Depends on context.
Yeah, depends on the context. Like apple and apple, you know, you capitalize an A, one costs €2, one costs 600, right? So, New York, is it one word? Is it 2 words? You know, we basically need to distinguish between what is a word and what is a token. In general, we say the output of a tokenizer, so the process of splitting is a token. And as your colleague was saying before, the meaning bearing unit is a word. That said, we are computer scientists, so we're sloppy with notation, we don't care. Sometimes we'll say that a word is a token, we'll exchange that as long as everything makes sense in our head, we're gonna be happy. Okay, so we know what a word is, but we don't need words, we need numbers. So we're gonna use something very simple, but for now very effective, which is called an average bag of words. So first we need to find words, right? So we go in the real world, we download a vocabulary and we collect all the words that are in that vocabulary. This is also can be done by a document, right? You scan Wikipedia and count all the unique words that you can find by splitting on white space and punctuation. Typical size, at least for this model that we're seeing, 20,000 to 100,000. Now it's a lot. Like, I don't want to give you false number. I don't remember the exact number, but now recent models we go over the level of trillion of tokens to train it. So if you don't know trillion, it's a big number. Check. Each word has a unique index in our vocabulary, and it's called a one-hot vector. Raise your hand if you know what's a one-hot vector. Oh, many people. Okay, so a one-hot vector is a vector which has only 0 except for one element. So it's a very sparse vector. What's the point? Is that if we have like a vocabulary of 1,000 words, we assign an index to each word in this vocabulary. So for example, the first word of the dictionary, I don't know, it's A, the article A, is going to be the vector which has as the first element 1 and the rest is 0. The second word we're going to have 0, then 1, and then 0, 0, 0, 0. We're going to see an example now. But basically, what we do is that if you have a document D, to obtain the representation of the document, we just sum the one vector and divide by the number of words of the document. Is it confusing? Is it easy? It's going to be easy with an example. Yeah, and here with D of Y means the word in doc D at the position I, and X of dy is the one vector. So let's make an example. Our document is just a sentence, a cat sat. So, and let's say we have X belonging to R3000, which means our vocabulary of 3,000 words. We opened a dictionary and we got the 3,000 most frequent words. That's our vocabulary, very simple. Now, our vocabulary is going to be something like that. So, for example, let's say the first element is A, then we have abandon, because it's the next more probable word. At some point, let's say in position 852, we have cat. I'm dying. In position 1,000, we're going to have a set, and then we have all the words until, I don't know, zebra, so on, to A, is going to be this vector, which has 1 only in the index of A, which is the first element, and the rest is all 0. Cat is going to be 0 everywhere, except for position 852, which is where in the vocabulary we have cat. So one not vector, very sparse, only one value, which is not 0. Sat, you can guess it, is going to have it in position 1,000. So what do? We sum it and average it, because if we sum these 3 vectors, we're going to obtain a vector which has 3, 1, so position 1, position 152, 852, sorry, position 1,000. Then we divide by the amount of words of this document. How many words does this document have? 3. So 1 divided by 3 is 0.33, and we will have 0.33 in those 3 elements. The rest is 0 divided by 3, so it's 0. Okay? Is it understandable? Is it clear? Raise your hand. Don't be shy. Yes?
Just leave it at these moments, the output vector. Why do we normalize it like that?
So the question is like, why do you need to divide it? It's just a convention and it's called average. So it's supposed to give you a kind of different it's supposed to give you a perspective of how often this thing is the document. Because now it's just a cat set, but it was a cat set with a cat who said, blah, blah, cat will become 2 or something, you know, and then it becomes more than 0.33. So in this case, it's useless because we have 3 words each occurring 3 times. But if you have a sentence of 40 words and one occurs 5 times, 1, 3, 1, 10, it tells you a rough idea, right? So, yeah.
But we could also use all vectors, like put them in a matrix and use this matrix as input to our model. I think.
I'll see you in like 20 slides.
Okay.
No worry. Yeah?
What is that? What do we get on the output? What is that vector X? What does it represent? What are we doing with it?
The vector X is representing a document. In our case, a document, which normally will be, for example, a review, is representing somehow the sentence a cat sat. Other? Someone? Yes?
It's not positionally encoded, right?
It's not positionally encoded. It has no information about where each word is. That's going to be a problem. We're going to see it soon. For now, we're going to try to deal with this because it was the first way people thought about transforming words into numbers. Anyone else? Okay, so I think we can go. So again, we have this cat set. Can we measure somehow how similar these vectors are? Yes and no. There is a thing called the Hamming's distance, which is by how many bits does the 2 vectors differ. But now if I ask you, how many bits are different between the vectors of A and cat? Someone, yeah, two, because one is one and in zero the other, and the other is one is like this one is different, and this one is different to somewhere here. Now, if I ask you what's the difference of how many different bits do we have between cat and sat? Yeah, two. And if I ask you how many different bits do we have between A and sat? Two. So it's a very simple measure, but it's also very useless because it doesn't really tell you how the word change, how multi-word expressions. So for now, we don't have any tool to really say how similar these things are, but we're gonna cover it in time. Out of vocabulary, if we decided we wanted 1,000 or 20,000 or 100,000 most common words, at some point we're gonna find a word that we haven't encountered, especially as language tends to evolve, and every year you make up new words or whatever. I don't know, maybe brain rot was not in the dictionary until some years ago. So this is because of the so-called Zipf's law, which tells us that the frequency of a word is basically inversely proportional to the rarity of the word itself. So basically, at the beginning, we have very common words, which are very, very frequent, and then the rarer the word becomes, the less frequent they become, okay? That's a problem. So when we use when we build a vocabulary, we use only the most frequent words. Why? Because we need to save space. We cannot have everything. So what happens when we meet a word that is not in the vocabulary? This is called out of vocabulary issue, and we're going to use a special token, which is UNK, unknown. Is there a better way? Can we solve out of vocabulary in a way which is not, let's just collect every possible word in existence? So,
often long words are an aggregation of shorter words, so we can have like segmentation within words.
We can split long words in sub-words. We're gonna actually see that now. Yeah.
Can we update the vocabulary?
Yes, we can, but that doesn't change that. So these all gonna be into a model, right? They're gonna retrain the model every time you have a new word from scratch.
That's my question.
That's a problem, right? So we have these things called byte-pair encoding. So what do? We split the words into characters. Like until we have only letters, and that's the basic vocabulary. It's gonna be 20 something, whatever, depending on the alphabet. That's your initial vocabulary. Then what you do? You count the two most frequent characters, merge them, and that's added as a new token into your vocabulary. Keep in mind, you don't delete the original character. Like if you discover that A, B occur very often together, you still have A and B, but you add AB as a single token. And you repeat that for a fixed amount of time. Every time you add a new token beyond the original size of the vocabulary. And if you do it enough with a large enough corpora, you basically get rid of out of vocabulary issue. So when do we stop? Like when do we stop merging? We run out of computation, we run out of space. There's no element, no pair of tokens which occurs at least 2 times or at least 4 times. You can just optimize how you want. So we're gonna see an example. We have this sentence, which is initially tokenized at the character level, because remember, our initial vocabulary is just every letter and the space. So this fat cat with the hat is in the cave of the thin bat. If you count, not gonna count with you now, but if you count, believe me, not crazy, TH is the most frequent pair of characters. So we're gonna merge into a single token, and if you notice now that this is not spaced anymore, is because this became a token. But I want you to notice that just because it became a new token, it doesn't mean that we don't have T and H as separated token. It's just increased. We're not replacing it. If you count again, you're gonna realize that A and T are the most frequent. We're gonna merge them. And now TH and AT, you see where this is going? It becomes much harder to have unknown words if we're starting to have sub-words, right? Because for example, I don't know, we have the word meaning. We never saw meaning, but from previous corpora we have mean and ing, for example. This works a lot with verbs, right? The continuous tense is just by adding ing to many verbs, so you can instantly tokenize. Yeah?
The spaces here, do they come as, do we take them into account?
No. In this case, the space is always a special one because we said that words are separated by spaces and punctuation, so never gets merged. But we're gonna see that can be done in another approach. Yeah.
So something like your word at any point.
No, it depends. If you run it enough, you may go to the point that New York becomes a single token. If you decide when to stop.
How if you don't take into account spaces? Because at some point.
No, sorry, you're right. Yes. No, it will never be merged because sorry, I wasn't thinking about that. You're right, it will never be merged. Continuing, you'll realize that THE, which is the previous token TH, and the single token character E can be merged. And so you get to these. And so if we stop now, our new vocabulary has just the letters. This is what we have in the beginning. And then we added these three new tokens.
Sorry.
Yeah.
Where do the TH in this come from then?
So what do you mean? Sorry. If you count here, if you take every possible element and count how often they occur, the most frequent is THE.
The question is more like we don't have any more tokens of T in there, do we?
No, but TH is now a token.
Yeah, exactly.
So you count not TH any. TH is a single element now.
Yeah, but we don't have any single T tokens in this example because we already merged it in. We have a singular H in hat, but there's no singular T in.
What I'm not getting the point. We're not considering the singular T. We are considering that we have. So at this point, let me do one thing.
I think the things you merge.
What it was talking? Yes.
They don't get thrown away out of the vocabulary.
No. Yeah, I clarified this. You're adding to the vocabulary. It's not because you have TH, T and H do not exist as single tokens. You're adding. See? They're all here, like T is here, H is here, but there's also TH. You're always only adding a new element. Okay. So there's a problem with byte-pair encoding. It's lossy. What do I mean? Well, we cannot always reobtain exactly the same sentence we started from because white space is basically this arbitrary special token, but it's not always that there's a space between the two words, right? So I'm gonna make an example in a bit, but how do we fix this? We use sentence piece, which is, for example, an alternative, which expands the white space as a normal token. So now we can also merge spaces. And what happens? As a note, there are many implementations of this, so we're not interested, but generally, this solves the issue. So if you take, for example, hello world, and after a couple of iterations, this is how sentence piece tokenizes. So you have hello space war LD period. Now, if we merge these, we obtain exactly the same sentence, while with normal BP, we may obtain maybe hello space word space something else, right? Because we have this rule that the words are separated by white spaces, but this means that sometimes we can add extra white spaces here and there. With this, since the space is encapsulated directly in the token, we can reach a lossless conversion. We can have an exactly identical text to how we started. Oh, sorry. Yes? Because now we have only hello world, but like I say that you have, I don't know, 5 words. My name is Charlie, you and I, with a comma. When you reconvert back to the sentence, you have this rule of adding a space between every word, which may give you extra space at some point. In this case, instead, The space is just escaped as a part of a token. So you just need to concatenate all the token, and then you get the original representation. Okay. Yes.
This for very, very long, on a long document.
Yeah.
A long document would be one singular large token.
No, because the whole document, I mean, unless it's a very bad implementation, because if the whole document becomes a token, you accept even stuff that occurs once. And by definition, the document occurs once within itself. So yeah, right? You don't go to the point you merge entire paragraphs. Usually you still stay under subwords. You may even put implementation. You say, okay, no token should be more than 5 or 6 characters or something like that. It really depends how you implement it. Okay, now we covered this properly. So we know how to convert our reviews into numbers and our labels into numbers. Labels are just 0 and 1. And the reviews, we can just use average bag of word. It's not great, it's not perfect, but it will do for now. Now we're gonna move to this juicy part. How do we build our actual vector model? So binary text classification. Recap, you're gonna see this a lot. We have f of x, which is x times w plus b. This is just this. You agree? Can you see how the product becomes? Yeah. And guess what? Let's talk about derivatives. What are the derivatives of f with respect to w, the generic weight, I? Yeah. Yeah, it's just xi. What's the derivative of f with respect to b?
1.
It's 1. Okay, so easy peasy. We're not too scared of this function. Easy to derive. I want to ask you a couple of questions now. Just to check if you're paying attention. Why is b a scalar and not like a vector? Yeah?
Because y is between 0 or 1, so because of that.
Exactly. Because in the end, what we want to obtain is a label. So after we multiply these matrix of vectors, we should obtain a number between 0 and 1. So it doesn't make sense that it's a vector. If we'll put something that returns 0, 1, 5, 0, 1, 5, or just a vector, it wouldn't make sense. Our labels is a single number, so we want to obtain a single number. Second question, why don't we also include in this the f with respect to x? Yes?
Find the output, the weights and biases.
Yeah, that's a bit. Let's try to explain it a bit more intuitively. What is x? The input. What is the input in our task?
Words.
Yeah, a review, right? Like a movie review. You don't want the model to train in a way that it changes the review. If you would include the x as a parameter, it would mean that your model says, oh, here's the review. It's positive. No, it's negative. Okay, let me change the review so it becomes negative. That's not the goal of the learning, right? So x is untouchable. Cannot be changed or learned or optimized, right? It's fixed. The review stays like that, so we don't need to derive it. So this function is unbounded, can be calculated from all values minus 11 plus 11, but I want the output to be limited to y belonging to 0 and 1. So how can we convert these to 0 and 1? So, this thing is going to produce a number, but this number can be 0, can be 3 million, can be minus 27. We want it to be 0 or 1. Who did not read the lecture or already knows the actual answer want to answer? Yeah?
Split it in the middle, then the negative numbers get 0, the positive numbers 1, and for 0 we have to get some convention.
Okay, that's good. So your colleagues propose, okay, let's take 0 as the neutral point, and then everything which is positive is 1, everything is negative is 0. That's what you say, right?
Yeah.
But the point is, how positive is enough positive? In your system, 300 billion is the same as 1.5. The same way that minus 50 is the same as negative as minus 300 trillion.
I thought that this is a plan of So we have to choose either 0 or 1 and not.
No, but that's the input. Once you put into this, and you multiply that by the weights and the b, you obtain a number, a single number, which is unbounded in plus infinite. So if you take this sum of products and you plug in values, random values into it, you realize you can obtain all kind of numbers. Doesn't matter if x is, first of all, x is not 0 and 1 only because it's averaged bag of words, right?
Yeah.
But even there, summing, you go over, right?
Y is element of the set of 0 and 1. This is what's on the Y.
No, y is exactly 0 or a number between 0 and 1, not a vector. It's a single number. You obtain 0, you obtain 5, you obtain 300. So your single setup, no matter how positive or negative the value is, I always say 0 or 1, which is not great because our model will need to understand how positive or how negative the things are.
I mean, it's just for notation because you say Y is limited to Y is element of the set of 0 and 1. That's what's there. So it's either 0 or 1 and cannot be in between 0 and 1. Is that true or correct?
No, it can be between 0 and 1. That means that in the
Technically, it's a different bracket, right?
yeah, okay, that's my. I'm gonna correct it. I'm gonna correct it. This actually can have all the mid values. Sorry for the result. You wanted to? Sorry. Yeah, gonna change that. So, yeah.
You can have like simplistically, what we can do is we can have a distribution on a graph of the slope in between and defining whether it on this side and this side can be distinguished as 0 and 1.
Yes. That's, for example, a valid option. There are many values.
I think they use activation functions to do that.
Yes, as I said, like, yeah, that's the next part. Yeah, I was asking for more preliminary things, but yeah, there are many ways to do this. But yeah, we use a specific one which has been tested and works, which is called an activation function, and usually we choose the sigmoid. So, what is the sigmoid? This is the sigmoid. Say hi to the sigmoid, and basically, its formula is 1 divided by 1 plus the exponential of minus t when t is the argument. What is the point? The sigmoid smoothly maps values that you give into it between 0 and 1. You can see the chart. It's basically a nonlinear function which is symmetrical, and the log linear model, which is the one we're training, does exactly that. We tokenize the text, so we obtain our average bag of words. We pass it through f, which is linear, so x1 w1 plus x2 w2 blah, 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 plus b. We obtain a value which is unbounded. It can be between minus infinite and plus infinite. And then we pass it through the sigmoid. So exactly this. Sigmoid returns a value which is between 0 and 1. No matter if you give it 1 million, it's going to be mapped between 0 and 1. If you give it 2, we're going to be value between 0 and 1. The cool thing is that it's smoothly. So extremely positive values will be much closer to 1, while less positive values, which is, I don't know, more closer to the center. So to give you an example, is like the sigmoid, which is derivative, and you can see as usual, our derivative gives us the direction. Now, how do we decide? Well, easy. If the sigmoid returns us a value bigger than 0.5, it's 1. If it returns us a value which is more smaller than 0.5, it's 0. If this is wrong, sorry. Oh, I'm gonna correct this. If we have exactly 0.5, you can use an heuristic. You can guess randomly, you can use the majority class, you can, I don't know, add a threshold, whatever you want. So the sigmoid is very cool and is very intuitive because you can actually interpret it as a conditional probability. It's not exactly the conditional probability, but acts as it because it gives you a number between 0 and 1. So basically, you can say that the sigmoid of your prediction is the probability of predicting 1 given x. So if it gives you 0.9, it's 90% chance that that's a 1. And if you complement it, well, you get basically the probability of a 0. So that's cool. Now we know how to convert our review in numbers. We know how to convert our review in numbers. We need what we feed this number to. And we also know that, since we have an infinite amount of values. We know to map them between 0 and 1 smoothly. So it gives us something that looks like a probability distribution. There's the only one thing to do now. How do we change W and B? So if you check that, yeah, I will need to go to BI. But if you know x1 W1 plus x2 W2, you can change the W's and the B in every possible way, and your model for the same review will obtain 30, -5, 1 million, which in turn will be turned by the sigmoid as 0.2, 0.5, 0.7. How do we find the values for which every review gives us the right output of the sigmoid? How do we train this model? We cannot do it manually. We cannot try changing W and B until we get the best result. So now we're gonna cover how do we find the best model parameters, and this is gonna close our loop on the neural networks. So we saw our basic log linear model. It can represent the data as numbers, and it can map the prediction to 0, 1. Again, I will say, how do we train the parameters theta, so that our model learns the best value? And we need a way to compare our prediction with the true level, because this will give the stochastic gradient descent a clear objective. You remember, we need a distance. Now we have a sigmoid, right? So we have an output which is between 0 and 1. Let's say we obtain 0.70, but the label is 1. Okay, we are kind of close to it. It would be 1, but it's not safe enough. We want, in theory, our model to predict 0.99 when it must be 1. And when it must be 0, 0.0002. So very well, but it needs to be very close. So we use a loss function, which is a function quantify how far our prediction is from the label. In the binary classification, we use this per instance loss. So for example, given a single case, like a single review label and our prediction, we want to obtain a number, which is a distance. Oh, I don't know, your prediction is 0.2 distant from the ideal one, or it's 0.8. You know, based on that, I adjust my weights. Then, given an entire data set, we just average this. And this is called the corpus-wide loss, which is this L capitalized. If you look at it, it's just all the losses we can obtain from every single example, so every pair of a review and a label, averaged over the entire data set. So I don't know, let's say you obtain 10 values of the loss, you divide by 10, and that's roughly your loss on the whole data set. So the training examples are fixed, you can change them, and we can change the parameters theta of our function to determine the loss. So the goal of our training algorithm is that we want to find the values of theta such that L is minimized. We get the possible lowest loss over the entire data set. So if on average, you know, we cannot be perfect, but if at some point by training our model is always within, wait a second, within 3 and 5% far from the ideal case, when you average, you realize, oh, crazy, like my corpus-wide loss is 3%. Like I cannot be worse than 3% away from the good prediction, which is great. I'll stop training. You want to ask something? What do you mean that there's the sigmoid?
Threshold where we say our prediction was positive.
Yeah, that's an heuristic of we apply to a sigmoid. Yes, it's after at the end. So if you have x, put it for the linear function. This is a number between minus infinite and plus infinite. Plug into the softmax. This return you a number between 0 and 1. That's why I
Threshold value to then train the model to then calculate the loss function.
Well, that's our decision boundary. Like the threshold we used 0.5 is just to say, you know, since the sigmoid gives us a value between 0 and 1, we're gonna say higher than 0.5 is 1, lower, you just split in the middle. The point is that we don't want to just make it barely. Like, what if you need to obtain 1, but you obtain 5,0,0,0,0,1. It's not great. You would like to obtain 0.97, right? Something like that. So we need to train that. That's why we need to train to get, sorry, to get as close as possible.
So we
Yes, use it, but you want the value even before the threshold to be extremely close. If you want the model to be very confident, you don't want to say 0.6. Oh, great, it's bigger, it's positive. The model is barely sure that that's a 1. You want it to become 0.90, 0.95, 0.97, right? Because then the model is extremely safe about that. We're gonna see an example later, practical, okay? So hopefully that will clarify. Okay, so once we define this, the goal of our training algorithm is to set the value of theta so that we minimize. So this can be seen as basically our parameter tuned, learned, are obtained by minimizing the loss over the whole corpus, the whole dataset, our 500,000 reviews, which is basically averaging the loss we obtain on every single review. So, okay, the bolting good. Can you think about an intuitive way to measure the distance? Yeah, we have 0.70. We should obtain 1. What's an intuitive way to, measure how distant the two numbers are? Let's see if there's anyone else. Wait, because you guys are very active. I want to see there's someone else. Okay, yeah. Yeah, one very simple one could be the absolute difference. Yes, you can.
So we have this loss function. I mean, this intuitive way is kind of easy, but I can think of more loss functions such as the squared loss capitalized for
So many mean averager, there are so many, right?
how much of the research is about timing, the vector loss function is about loss function engineering. Do you see the big gains in the picture, or is that something that is basically solved?
So how much of how much of research is finding good loss function? So it depends. If you're doing, more high-level research, like trying to improve the data or the large language model, not really. We have a lot of loss functions which are very well known. They work well. Heavy machine learning, when you go to, proving the mathematics of it, yes. There's also an entire domain called loss landscapes, which try to measure how the entire domain of the loss function is, and if you can optimize it even more. That said, there is like, I think, a video when they made the Minecraft loss function, which is basically a function that draws something related to Minecraft and it eventually converges. Like almost anything can be trained if you throw enough time into it. But yeah, there is line of research of understanding. That's the main reason why we know that some functions are better than others.
Is this area where you see the path towards the AGI, or is this something very minor where you can rather get marginal improvements? Like how much from 0 to 100% do you think will this matter in the future?
Oh, that's how much from 0 to 100%? I think improving the loss will lead us to AGI. First of all, I don't believe in AGI. I think it's business jargon, so I cannot answer to this question. But we can discuss maybe after the lecture because so we have this function, the absolute value of the difference, but it's not ideal. Why is not ideal? Because we need a gradient which is useful, a gradient which gives us the direction. And first of all, this function is not differentiable in 0, but that's okay. We can make up something. We can say in 0, we assume a value, whatever. But still, look at the derivative, how it's defined. Where do you move? Well, how do you move in your stochastic? You remember we have this function, we follow the tangent to minimize, but where do you move? The derivative is 1 of -1. It's basically almost like, it doesn't tell you anything. This doesn't mean that we cannot learn with this function, but it's gonna be extremely slow. Like at this point, it needs to bounce and keep trying, it's like, it's not great. So we need something better. So there is something better. Yeah, it's called the binary cross entropy loss. It's very famous. It has this formula. And do we know how to optimize this function? Of course, we know stochastic gradient descent. We can decompose any function. We can calculate this gradient. Once we calculate this gradient, we can minimize it. And now the picture is complete because our model becomes like this. So we have our learnable parameter, WD, this change can be changed during training. And then we have our input, the review. We plug everything, we obtain a value between minus infinite and plus infinite. We plug into the sigmoid, this becomes between 0 and 1. And this guy here, the binary entropy loss, tell us how distant our prediction is from the actual label here. It's like 0 or 1. And once you have that, we backpropagate, we adjust the weight to minimize the loss until we are done. I'm going to show you now something a bit more practical. I'm going to show you a visualization of a logistic regression actually acting. So let's say you have this, but basically you're going to see this space where we have 2 points, and these 2 points are clearly, what is wrong with this screen? Okay. You know, the blue may be positive and the 0 may be negative. This automatically trains the model, so you don't need to follow the mathematics, so it automatically calculates the loss, which is the binary cost entropy, and it shows you where the decision boundary is. And you're going to see that for now, nothing changes. Why? Because the decision boundary is here, and these are super, super close. We are super confident, right? It will be super close like this, they will need to change more. But you're going to see that now, at some point, we're going to get a red point, and the red points are much closer to the decision boundary, which means our model classifies almost everything as 1. Now, if we have this red, we recalculate, and the decision boundary, in a second, gets moved just above that point. We're still not great because these points are already all misclassified. Everything above this line is 0.5, is bigger than 0.5. So we still have some negative points. Again, this is barely classified correctly. And so the network is gonna move the decision boundary. Now we're kind of good, but still all red points are barely classified as negative. We want ideally to go to the center. And if you give it a bit of time, I don't remember, this video is long. If you give it a bit of time, we're gonna shift to a 3D visualization. Yeah, where we can actually see the sigmoid curve. So you can represent this decision boundary also as the curve of the sigmoid, which gets adjusted when we update the parameters. So you see that every time we're moving a bit more because we want the model to be extremely confident. In this case, I made an ideal case. The decision boundary, if you put it exactly in the center, is equally distant from the points, right? But you know, at some point, you're gonna finish the time of training, like you cannot get the best possible solution. There's always a best solution unless the problem is trivial. But yeah. So now we can complete our algorithm that we saw in the previous lecture, which is the stochastic gradient descent, the online version. What do? While we don't meet stopping criteria, which could be number of iterations, we run out of memory, whatever, we run out of time, whatever, we select pair, like a review and a label. We compute the loss of the prediction, so applying f to x and obtaining a y hat. Remember that, let me do this. This, it's y hat, basically. F of xi theta is basically like x, y, wi plus b, okay? The gradient is basically the gradient of the loss with respect to our parameters. We update theta by, you know, our usual learning rate, and we return the new parameters. This is new model, and we keep doing this again, and again. So basically, we calculate the loss for a single training example, and these are rough estimate. The problem is that we're not averaging, and the gradient can be noisy. Basically, you're updating the model every single time. First of all, can be slow, depending on your setup, but also the gradients can be noisy and even inaccurate. So this is good to use only when you have some computational limitation or when you need to, you know, continuous learning. Is the setup when you basically don't have a data set stored on the disk. The data are arriving in real time. Like, for example, a new review arrives every 5 minutes. So you cannot wait. An alternative is the mini batch stochastic gradient descent, which is exactly the same, but you sample a certain amount of training example. And what do? Basically a for loop where you compute the loss and then you average the loss obtained over the m examples. And this is a bit more mature because of course you can vary m. If m becomes 1, you're back to online stochastic gradient descent. And if m is equal to the whole data set, basically you do one step on with learning. And it can be parallelized, which is great. So now, basically learned all of this. We know how the data gets transformed. We know how the model gets instantiated with, the sigmoid. We also know how we change theta. So by doing this backpropagation with respect to the loss, yes? This one?
So the sampling of the examples, is it uniform or maybe we sample so that the labels are like more uniformly distributed or?
So do we sample uniformly or do we sample like in a specific way? Up to you. There are different things like you can randomly sample or, if you train for enough epochs, if your training goes along for enough, you may assume the random sampling works because you're sampling so many times, right? But that said, nothing prevents you from doing some stratified sampling or sampling focused on how your data set is. For example, if you have an healthcare data set and there's a very rare condition that occurs only 1% of the examples, you may want to balance because the risk is that you almost don't see it during training. At the same time, you want to make sure that you also have enough example to pick for the test set because those do not let the model train. Yeah.
We do that, but we have to make sure we don't bias towards that condition. It's very right, so we don't overpredict it.
Yes, we also don't need to overpredict. It's all a matter of what do you say? Compromise, not to balance, basically. The trade-off. Yeah, that's the word I was looking for. Yes, we can move a bit. To the quiz, I mean, we can move. Okay, so let's resume, guys. Let's do something fun. Let's train a network by hand. So consider a neural network which is super basic. Okay, we have only one weight and one bias. So basically it does XW plus B. And we want to do binary classification. So yeah, this is our function, XW plus B, only one weight, no W1, W2, W3000, one weight. And we have our sigmoid, which is as usual is. And this time I'm using this loss function, which is a very stupid one. It's not ideal, but it's easy to calculate, so it's gonna serve our purpose. So it basically say the prediction minus the label squared divided by 2. Okay. Let's assume we have this dataset pair. So x1 is just a tree, a single number. We're even going to the point that we don't even have vectors. We only have numbers somehow. And the label is 1. So we want our model to, obtain a number after doing XW plus B. The sigmoid is going to map it between 0 and 1. And ideally, we want to obtain 1. And let's also say that we have initial parameters. So let's say that W1 is 0.6 and B is 0.2. This can change. This can become 0.8. This can become 0.4, depending what the loss tells us. Oops. So our network is going to be like this. We have the loss function, which takes in input the true label, but also our prediction, which is the output of the sigmoid, which is obtained by passing on the sigmoid x hat, which is the result of our function, which takes our parameters and the input. Okay? And now to scare you, we're also gonna see all the derivatives. You don't need to know this, no worries. I mean, if you check, you're gonna realize it's kind of easy to obtain, but it's just for showing. Okay. Iteration 1, again, we have these values and these data set. What do we do first? Forward pass, which means we insert the data, calculate everything. So XW plus B is 2. So if you go like basically B before, we had only xw plus b. If you do this by hand, you obtain 2. The sigmoid, if you calculate it, gives us about 0.88. So that's good. We're already fairly close, right? Because we should obtain 1. We have 0.88. It's not perfect. I don't know, it would be better if it would be 0.99, but still, it's not bad. And if you calculate these things, so you divide it by 2, these minus these elevated to the square, you obtain 0.007. So the laws tell us this kind of notion of distance, which kind of tell us we are pretty close, right? If it will be 0, it will be perfect, but it's not. Now we do the backpropagation pass. So we calculate the derivative of loss with respect to W1 and B, which are the only parameters we have. If we calculate these, you know, apply the chain rule and calculate it, we obtain that x1 is minus 0.04 and sorry, not x1, sorry, the derivative is minus 0.04. And these are the derivative is minus 0.01. These are our gradient. What do we do now? We update the parameters. So the first one, since is the derivative with respect to W1, is going to update W1. So we're going to get the original values minus a learning rate. Did I find the learning rate before? Sorry. Oh, damn, I don't remember what learning rate I put here. Can I back derive it from here? Is that minus this? I don't remember actually. Sorry, guys. This I didn't notice this, but eta is a number that I need to pick up from the previous lecture. Sorry, I will update the slides on Moodle. But basically, if you multiply this 0.6 minus your gradient times a constant which is unknown, and I will add later, I'm sorry, you obtain 0.62. So what happened? We changed the parameter just a little bit. Which, is it bad? No, it kind of makes sense. We were already pretty close, like the loss is very low. So it makes sense they change, it's cautious, they change just a little bit. If we obtain, I don't know, an enormous loss, probably would have changed it much more because the gradient must be much bigger. The same for this. If you calculate this difference according to the formula, you obtain that we changed slightly. But did it do anything? Yes?
The note for the second part of the update, it should be divided. Like right now, you're updating the weight.
Oh my God. Oh, you're right. Guys, really sorry. I'm gonna change this. So this is B, of course. We're not changing the W. Thank you for the correction. Now we did this. So what? Where's the magic? Oh, here's the magic. Now, if I try the same thing, so I take exactly the same point, 3 and 1, but with the new parameters, and I calculate the loss, it's lower. It's 0.006. So I'm optimizing. Do it again and again and again. The loss is going to become less and less and less. Of course, this is not how it happens. I don't immediately try on the same point. I will sample another point and continue, or sample 10 points, then another 10 points. And, you know, the more you do this, the lower the loss gets, and we'll keep train our model. Yes?
Which part of this process is the gradient then, the backpropagation has?
This is calculated the gradient, and this is the final part of the backpropagation where we update, because, you know, in the backpropagation, we update retroactively the parameters based on the gradient and the learning rate.
So the gradient is the minus 0.04, for example.
Well, one of the elements. We have the gradients, in our case, depends on W1 and B.
So we have two gradients.
Okay, two elements which overall constitute the gradient.
Sorry.
We have two elements which constitute the gradient as a whole. Okay. Any other? Okay. Don't know if I'm very good or if you're exhausted. We're gonna close now with the last part, which I promise you is gonna be kind of short. Okay, we don't care about binary classification. Now we want to extend to 6 classes, 3,000 classes. You know, let's say we want to calculate the general. of the movie. We want to classify if it's a horror movie, if a thriller, so it's not 0 or 1, right? So there is no ordering. Okay. I guess this is my life now. Okay, let's give an example. We want to classify the language of a document. So let's say we have 6 classes. We don't know so many languages, so we're gonna just calculate if it's English, French, German, Italian, Spanish, and all the rest gonna be other. Okay. Well, the labels now cannot be like, okay, they could be 0 to 6, but that's usually not how we do it. Why? Because the sigmoid is great for calculating between 0 and 1. We don't have a function that symmetrically maps things from 0 to 6. It's a bit weird, and we will have lots of weird mid-thresholds. So let's just say we're going to use a different one-hot vector for each label. So English as the first element as 1, French as the second element as 1, blah, 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 blah. How do we expand to multi-classes? Okay, before we had this vector, you know, the input, what's a way? Let me see if there are other people. 4, someone brave. I'm gonna give you a bonus if you resent. No, I'm gonna do. Yes? Well, we could use matrices. Yeah.
We could break it down into a series of binary classification classes.
Yeah, we could actually try to classify one at a time, similar to what we saw with the classification, the confusion matrix in the first lecture. Okay, both are kind of fine. So let's start from yours. Let's consider each language and let's have a weight vector and a bias for each single language. Then we can predict the language resulting in the highest score. Basically, you have 6 different log linear models. All of them will give you a score between 0 and 1, and you just pick the highest one. But this means that I'm taking x, multiplying it by a weight vector, and summing a bias. Then I'm taking another vector for French, summing with a bias. Then I'm getting another vector for Deutsch, and summing to a bias. Then I'm getting another vector. So you see where this is going, right? Why don't we just use a matrix, as your colleague said? Why do we need these 6 separate vectors? Why don't we unify it? So we can rearrange the different W vectors into the row columns of the matrix W, which now will have as a number of row the die in, which is, for example, the size of the vocabulary in our case, and as columns, the target classes, which are 6 in my case. And then we have a vector, which has only 6 elements. So we get this. So you can see basically every column of the matrix has as many items as the elements of our vocabulary. And overall, we have 6 of these columns, 1 per language. Now, our function becomes like this. Again, we have W with this dimensionality. In this case, the out dimensionality is 6. Why? Because you have 6 languages. I mean, 5 plus the other class. And this is the simplest neural network, which is called a linear perceptron. You may remember for the quiz on the first lecture that we talked about this. This is that guy. Then what happens? Well, we'll obtain, a value like this of 6, a vector of 6 elements. We just pick the element with the highest value, and this tells us the index in the one-hot vector. So, for example, if we obtain that y at, which is the argmax, is 3, which means, okay, the third element of the vector has the highest value, we obtain the language which corresponds to the third element, which is Deutsch. Okay?
Question.
Yes?
This grows linearly with the number of languages we're trying to predict. Is there any better way? Because it seems that this could be an issue if you have like Boolean labels or something.
Yes, so you're saying that it scales a lot with parameters, right? If you have 50 languages, it becomes enormous. That's what you're asking, right? Yeah.
So is there a way to use this in sublinear time?
there are, but we're gonna cover later. I mean, not today, but in later lectures. Like today, we're focusing on the basics. But you're right, it explodes, right? Depending on how many languages there are in the world. I cannot even count. If you can't count the Indian ones, probably it's already like, you know, I don't know if you know, like in India, you move 2 meters, you change language, not even dialect language. It's crazy. One important thing about this is that we are learning representations, which is one of the core things of machine learning. So X is a document representation. Do we agree? Is the representation of our document in English. So it's when you contain our average bag of words, it's a document represented somehow. But the prediction is also a document representation. It's just more specialized on this task, right? Basically, it's a representation on how the document is represented in different languages. We obtained maybe, you know, it's Deutsch, so it is a representation of that initial document. Just tell us that it's focalized on which languages it is. But the matrix can also be seen as a representation, depending how we watch it. So, you know, the matrix has this structure. The columns are the language related to the languages, and the rows are connected to the words in the vocabulary. So that's how we frame them. So if you consider the columns, is telling us how each language is composed based on its tokens, right? Basically, you're gonna have like, you know, some words like maybe, I don't know, mozzarella, maybe more common in Italian, or bratwurst, which will happen basically almost only for Deutsch. I don't know, being very stereotypical now. If you consider the rows, is telling how each token is represented in each language. Because for example, bratwurst, if you go on the row of bratwurst, is going to have values, and probably those values be more meaningful for Deutsch and less represented in other. So you remember we have this averaged bag of words, right? Now when we move to this setup, what happens? What happens when I multiply my average bag of words by this matrix, which is called the embedding matrix, by the way? Let's ignore the bias term. Nothing changes, just a sum at the end. But basically, you have this, okay? Again, you should have these. No, let's ignore it for now. Let's be lazy. This is nothing more than the average bag of words that we know the formula, you know, sum the one of vectors divided by the number of words in the document, multiply for a matrix. I'm gonna do a little trick. I'm gonna put the matrix inside. Can I do? Yes, by distributivity. It doesn't depend on the sum, so nothing changes. If it's not clear, see again the distributivity property. Now, this is one-hot vector. What happens when I multiply a one-hot vector by a matrix? You know, if I multiply a vector which has all zeros but one element 1, and I multiply by a matrix, what happens? Sorry?
It becomes a vector.
Yes, but
You get a scalar of that index.
what do you mean a scalar of that index?
Basically, the value, the element on that index.
You don't get a scalar. These are matrix, you won't get a scalar. You won't get a single value. You will get that you select a specific row of the matrix. Now, if you try at home, take a one-hot vector, in whatever you want, and you multiply by a matrix, you realize that what you obtain is exactly, if the one-hot vector has 1 in the third position, you'll obtain as a result the third row of a matrix. It's acting as a selection, because all the rest will become 0. And yeah, so this is nothing more than the row, the row in position I of the matrix. So this continuous bag of words, that's what we call it, can express either as summing word representation vectors, as we saw before, but also by multiplying the vector by a matrix in which each row corresponds to a dense word representation, and we call it again the embedding matrix. So this cool thing that, you know, like the vector just selects the most relevant column, right? If it's German, it's gonna, you know, select that one, or sorry, the word, depending on the word, not the language. Or the fact that if you consider the matrix by rows and columns, you obtain, oh, this is what words are more typical in German versus how this word is represented in 6 different languages. this is the actual central point of deep learning. And you can say that basically one of the main power of it is like learning good representation. We're gonna cover a lot of representation in our course. Now, okay, we changed the input. Our model expanded to a matrix. We can handle 6, 10, 2,000 classes. But we need to turn this into probabilities. Because again, we don't want a vector of numbers when you know English is 1, Spanish is 3 million, Deutsch is -20. Okay, it could work, but it's not intuitive. It's not easy to understand. I have to stop with this. Okay, how do we turn this vector into a distribution of probability? Because before we have the sigmoid applied to a number, what do we do? What do we do? How do we transform a vector now in probabilities? You know too much. I don't, yeah? You know the answer already, but yeah, I want to guide you by use softmax. But you know, one may think, let's just apply the sigmoid to each single element, right? Sigmoid returns me a value between 0 and 1. Can you tell me why this doesn't work? Someone can want to raise their hand and guess why applying a sigmoid to every single element? Yeah, exactly. It doesn't end up to 1. So a probability distribution, if we sum all the elements, will be 1. You know, you cannot have more than 100 probability, 100% probability of something. So we use softmax. This is the softmax, and basically it takes a vector. You can see it's very, very familiar in its shape, it's similar to a sigmoid. The denominator is a nonlinear bijection from, you know. And at the denominator, we have a normalizing constant. So we make up that everything sums up to 1. Interesting enough, you can also do something with softmax. You can smoothen it with something called the temperature. So if you play with large language model, you know there's this thing called temperature. Does raise your hand if you know temperature? Okay, so you raise your hand? No, you are less.
No, I know what it is.
What happened when you change temperature?
Let's say the creativity of
The creativity of the model increases, right? Creativity is it produces more varied outputs. Why? Because when I smoothen out this is just the softmax divided by t, what happens is that I flatten the distribution. So you can see here how the distribution of predicting a specific value changes when I increase the temperature. So you see that if I have like t temperature equal to 1, 1 is still kind of most probable. If I increase to 100, they all become equally valid. So what you're doing is making the model more, you know, in a way more uncertain on which element you should pick. Now it's not particularly useful, but we'll see when we go to large language model how this can be cool. And for the loss function, I'm gonna be quicker. You have a vector of ground truth labels. So the ideal probability distribution, like, you know, ideally would be all 0 except 1, 1, like Deutsch or Spanish. And you have a vector of your predictions. You use this, which is the cross entropy. Now, if you do your homeworks and maths at home, and you compare this with the binary cross entropy, you realize this is exactly the generalization of the binary cross entropy to n classes. Just you can go from one to the other. And this is almost the end